Welcome to True Projects. In this video, we are going to explain about the project entitled as Optimizing Breast Cancer Mammogram Classification Through a Dual Approach, a Deep Learning Framework Combining ResNet 50. So before getting into the video, let me give you the brief description about the project. This project focuses on improving breast cancer detection from mammogram images using a dual deep learning approach. It combines ResNet 50 based feature extraction with both classification and detection strategies to enhance accuracy, robustness, and reliability in identifying cancerous abnormalities. Coming to the abstract states that this module explains the overall objective and motivation of the project. Breast cancer is one of the most life-threatening disease among women, and early diagnosis plays a vital role in reducing mortality. Mammography is the standard screening technique that manually analyzes is time consuming and prone to human error. To overcome these challenges, the proposed work introduced a dual learning framework that leverages the ResNet 50 architecture for automatic mammogram classification. By combining deep feature extraction and optimized classification strategies, the system aims to improve diagnostic accuracy, reduces false predictions, and assists radiologists in making reliable clinical decisions. Coming to the existing system mainly depends on traditional image processing techniques and convolutional machine learning algorithms such as SVM, KNN, and random forest. These methods rely on handcrafted features like texture and shape, which requires expert knowledge and often fails to capture complex patterns in mammogram images. Even some early deep learning approaches use single CNN architectures, leading to problems such as overfitting, limited generalization, and reduced performance on low constraint or noisy images. As a result, existing system often produces inconsistent and less reliable diagnostic results in real-world medical environments. Coming to the proposed system or base paper work, the proposed system introduces a dual approach deep learning framework centered around ResNet 50. ResNet 50 is used as a backbone network for extracting deep and discriminative features from mammogram images, effectively addressing the vanishing gradient problem using residential connections. The dual approach enhances learning by combining fine-tuned deep features with optimized classification layers. This results in improved accuracy, robustness, and generalization across different data sets. The system is designed to act as an intelligent decision support tool for radiologists, enabling faster and more reliable breast cancer diagnosis. Coming to the dataset information, we have used two different datasets. One is KAU BCMD mammography classification dataset, and second one we have used mammogram FAMRJ detection dataset. First, KAU BCM mammography classification dataset. This dataset is used for classification task. It contains 5,662 mammogram images collected from 1,416 patient cases. Each case includes standard clinical views, craniocaudal and mediolateral oblique for both breast. The images are labeled according to BI-RADS category and including clinical metadata such as age, breast size, and view type. Annotating and verified by expert radiologists, the dataset supports both JPG and DICOM formats. This dataset is ideal for training deep learning classification models such as ResNet 50 to distinguish between benign and malignant classes. Next, Mammogram FAMRJ detection dataset. This dataset is used for the detection task. It contains approximately 1,486 mammogram images with bounding boxes annotating that highlights suspicious region such as tumor or masses. The dataset supports object detection tasks and is compatible with YOLO-based models. Unlike classification dataset, it focuses on localizing abnormalities within images, making it suitable for training detection models that visually identifies cancer affected regions. Coming to the novelty, or extinction or enhancement or improvement. The novelty of this work lies in extending traditional classifications by introducing class-wise data augmentation and balancing techniques, multiple deep learning architectures, exception, ResNet 50, and a hybrid exception plus ResNet 50 models are evaluated, with ResNet 50 achieving up to 91% of accuracy. YOLO-based detection models are integrated to localize abnormalities in mammograms. Furthermore, explainable AI techniques such as GradCam are used to generate heat maps that highlights important regions influencing model predictions. Additionally, a Flask-based web application is developed to allow users to upload images and receive predictions through a user-friendly interface. Coming to the flow of the work, first we have dataset preparation. The datasets are prepared separately for classification and detection. Classification uses labeled mammogram images, while YOLO detection uses bounding box annotations in YOLO format. The datasets are split into training and validation sets. Next, visualization. Class distribution is visualized using bar graphs and sample labeled images and displayed to understand data balance and label quality. Next, pre-processing. For classification, data augmentation techniques such as rotation, flipping, zooming, and brightness adjustments are applied. Labels are encoded, features are extracted using ResNet 50, and class imbalance are addressed using SMOT. For detection, a data.yaml file is created for YOLO with class names and path. Next, model training. The classification branch trains ResNet 50 with an MLP classifier and evaluates extended models including exception and hybrid architectures. Minority classes are oversampled using augmentation. The detection branches trains YOLO V5, YOLO V8, and YOLO V11 models to localize cancer regions. Next, evaluation. Classification models are evaluated using accuracy, precision, recall, FN score, confusion matrix, and ROC AUC. YOLO models are evaluated using MAP, precision, recall, and different YOLO versions are compared. Next, interference pipeline. Giving an input mammogram image, the system output bounding boxes indicate suspicious regions and predict the breast cancer classes. Next, a Flask-based web application is implemented. Users upload images through a front end. YOLO detects regions of interest. Classification models predict cancer type. The results are displayed with confidence score. The algorithms used are exception, ResNet 50, and hybrid, which consist of exception plus ResNet 50. And as an extension, we have used YOLO based classifications like YOLO V5, YOLO V8, and YOLO V11. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, firstly, you need to copy the path of the code folder from the address bar of the file explorer. Then open Anaconda prompt. By using the command cd followed by a space, paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py. In the Anaconda prompt, this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it in any web browser. I prefer Chrome. So this is the homepage of the project should now be displayed in the browser. In this page, we have home button, login button and register button. Firstly, click on register so that the create account page will be open where we need to enter the details and create the account for user authentication like username, full name, create a password, contact number, mail ID. Then click on sign up so that all the given details are stored in signup.db and login.html will be opened where you need to access the application with the help of username and a password. Then click on login so that the prediction page has been displayed. In this page, we have prediction button, graphs button, notebook button and logout button. Firstly, click on prediction button as we are dealing with classification and detection. So first let us go with classification. When you click on classification button, the upload image for prediction will be open where you need to upload the image and predict. We have uploaded the image and then click on predict so that the input image is pre-processed and the output will be displayed as BIRADS1 negative. The model confidence level is 61.45%. We also have the visual analysis like original mammogram, GradCam heat map, and overlay visualization. We also have the category information like the description, risk level, follow up timeline, and additional content. And we have medical guidance and recommendations like precautions, recommendation, and suggestion. Now click on another image so that again the uploadation will be opened where you need to upload the image and click on predict so that the input image is pre-processed and the output is predicted as BIRADS3, probably benign. The model confidence level is 87.52%. We also have the visual analysis like original mammogram, GradCam heat map, and overlay visualization. We have the category information and medical guidance recommendation for that. And now let us click on analyze another image so that the form will be opened again where you need to upload the image. Now let us upload the image and click on predict so that the input image is pre-processed and the output is predicted as BIRADS4, which means suspicious abnormality has been detected. Model confidence level is 99.7%. We have the visual analysis, category information, and medical guidance and recommendation. And again, click on analyze another image so that the form will be open where you can upload the image and click on predict. The input is pre-processed and the output is predicted as BIRADS5, which means highly suggestive for malignancy. The model confidence is 100%. We have the visual analysis, category information, and medical guidance and recommendation. Now click on view analysis. Now click on analyze another image. As we have checked the classification, now let us check for detection. When you click on detection, the upload image for detection form will be open where you need to upload the image and detect. The image has been uploaded. Now click on detect so that the input image is pre-processed and the output is displayed as normal for the given image. Now click on view analysis. Now click on analyze another image so that form will be open where you can upload another image and check the output for detection. Now click on graphs button so that classification and detection graphs will be opened. Let us check one by one. First, classification. When you click on the classification, the graphical representations of the classification will be opened. First, we have image count per class graph. The graph highlights a significant class imbalance in the data set. BIRADS1 dominates with 1,865 images, while BIRADS3 and BIRADS4 have substantially few samples. BIRADS5 is extremely underrepresented with only 24 images, which may impact model training and performance. Next, we have confusion matrix and ROC curve graph. The confusion matrix shows that the model correctly classifies most BIRADS1 and BIRADS3 images with very few misclassifications. Some confusions is observed between BIRADS3 and BIRADS4, likely due to visual similarities and class imbalance. BIRADS5 has limited samples, which affects prediction consistency. ROC curve resonate 50 graph. The ROC curve indicates stronger classification performance across all classes. High AUC values demonstrate excellent discriminative ability of the model. Next, we have training accuracy and training loss graph. The training accuracy steadily increases across epochs, reaching nearly 100%, indicating effective learning. Validation accuracy remains consistently high, with minor fluctuations showing good generalization. The small gap between training and validation accuracy suggests limited overfitting. Training and validation loss resonate 50 graph decreases sharply, conforming stable convergence. Training loss decreases sharply, conforming stable convergence of the model. Validation loss initially decreases but slightly fluctuates in later epochs, indicating mild overfitting. Overall, the loss trend suggests a well-trained and reliable model. Next, we have accuracy of all models graph. The bar chart compares the accuracy of different machine learning models. The proposed full balanced model achieves the highest accuracy, close to 100%, indicating superior performance. ResNet 50 and proposed trained balance also show stronger results, while exception and the hybrid ensemble perform slightly lower. Overall, the proposed approach outperforms the baseline and ensemble models. Next, we have FN score graph. The bar chart illustrates the FN score performance of different machine learning models. The proposed fully balanced model achieves the highest FN score, indicating an excellent balance between precision and recall. The hybrid ensemble and resonant 50 model shows moderate performance, while exception and proposed trained balance have comparatively lower FN score. Overall, the proposed balance model demonstrates the most reliable classification performance. Next, we have recall of all models graph. The bar chart presents the precision score of different machine learning. The bar chart compares the recall performance of YOLO V5, YOLO V8, and YOLO V11 models. The graph compares the recall performance of different machine learning models. The proposed fully balanced model achieves the highest recall, indicating the best ability to correctly identify positive cases. The hybrid ensemble and resonant 50 model shows moderately recall performance. Exception and proposed trained balance have lower recall, suggesting more missed positive samples compared to the proposed model. Next, we have precision of all models graph. The bar chart presents the precision scores of different machine learning models. The proposed fully balanced model achieves the highest precision, indicating the lowest false positive rates. Proposed trained balance, exception, and the hybrid ensemble shows comparability and moderate precision levels. ResNet 50 has slightly lower precision, suggesting more false positive predictions compared to other models. Now let us check the detection graphs. First, we have recall of all model graph. The graph compares the recall performance of YOLO V5, YOLO V8, and YOLO V11 models. YOLO V11 achieves the highest recall, indicating superior ability to detect relevant objects with fewer missed detections. YOLO V5 shows moderately recall, while YOLO V8 performs slightly lower. Overall, YOLO V11 demonstrates the most effective detection capability among the three models. Next, precision of all models graph. The graph illustrates a comparison of precision values for three YOLO object detection models: YOLO V5, YOLO V8, and YOLO V11. Among them, YOLO V5 achieves the highest precision, indicating it produces the most accurate positive detections. YOLO V8 performs slightly lower but remains close to YOLO V5, while YOLO V11 has the lowest precision of the three. Overall, the chart shows a gradual decrease in precision for YOLO V5 and YOLO V11. Next, we have MAP graph. The graph represents the mean average precision of three YOLO models: YOLO V5, YOLO V8, and YOLO V11. YOLO V8 achieves the highest MAP, indicating the best overall detection performance among the models. YOLO V5 performs very closely, showing comparable accuracy. In contrast, YOLO V11 has a noticeable lower MAP, suggesting weaker detection capability in this comparison. Next, click on Logout. So finally, the proposed dual approach deep learning framework effectively improves breast cancer mammogram analysis by integrating ResNet 50 based classification with YOLO based detection. The system achieves higher accuracy, better localization of abnormalities, and improved generalization across dataset. The inclusion of explainable AI and a Flask-based web application further enhances model transparency and usability. Overall, this framework serves as a reliable and efficient decision support tool for early breast cancer diagnosis. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.